So far, we've been considering acids or bases, but as we start to move along in this course, we'll start to think about what happens whenever we mix an acid or a base. So what we're going to do today is start to kind of look at a qualitative view of this and start to make some predictions and really start to compare Kas and Kbs. So as we do move forward, one of the things that we will assume for this unit at least the end of it, we'll say that the concentration of the acid is equal to the concentration of the base. And we would say that is equimolar. So as we start to move along, what we're going to see is that acids neutralize bases, and we get an ionic compound to be formed. So if we were to look at the case of a strong acid and a strong base, we'd have something that looks like this. Our generic strong acid, plus then we'll have a strong base with one hydroxide. So we'd end up with something that looks like this. We'd have H2O, and then we'd have something that has the cationic component from our base, and then the anionic component from our acid. And this is what we would call a salt. So we can actually tell quite a bit about the reaction based on what salt is present or what ions are present. So as we go forward, what we're going to look at is if you mix a strong acid and a strong base, and again, we're making this assumption right here that the concentrations are equal, that you'll end up with a neutral solution. Whereas if you were to mix a strong acid and a weak base, this shouldn't come as a surprise, but you would end up with an acidic solution. And if you mix a weak acid and a strong base, it would be a basic solution. And then I guess the real question would be, well, what happens whenever you mix a weak acid and a weak base? Is it going to be neutral? Well, is it going to be acidic? Is it going to be basic? Well, it really depends. And that's one of the questions we're going to attempt to answer in a future lesson. So one of the things that we're going to look at is salts that yield neutral solutions. So if you have a strong base, your cation is going to be an alkali or an alkaline earth metal, with the exception being beryllium. And if you have a strong acid, these are some of the common anions that you'll see: chloride, bromide, iodide, nitrate, or perchlorate. And these would come from hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and then perchloric acid. These are just a few of the strong acids, but these are the most illustrative that we'll look at. So what will happen is if you see something with an alkali metal, so you maybe have a solution that has sodium ions, and then you could take any of these anions. So if you had sodium nitrate, this would indicate to you that the solution is going to be neutral if the acids and bases were added in equimolar proportions. So it could be any of the alkali or alkaline earth metals except for beryllium, and then these are the anions that we will look at. So just keep that in mind as we move along. So let's go ahead and start to consider a proton transfer reaction. So think about this. If you have NH4Cl ammonium chloride, this comes from the weak base ammonia and the strong acid hydrochloric acid. So if you were to think about this, we have ammonia plus hydrochloric acid yields ammonium chloride. Okay, so this is a weak base. This is a strong acid. Well, ammonium chloride could actually dissociate. If it dissociates, what we're going to end up with is we'll end up with our ammonium ion and our chloride ion. So we know that the ammonium ion, this behaves as a weak acid, and this chloride anion, remember that this is what we said previously, this anion indicates that we have an acidic solution. Whereas if we were to look at another example, so here we're looking at sodium hydroxide and then hydrocyanic acid. So we have NaOH plus HCN. yields sodium cyanide plus H2O. So here, this is our salt, and this will dissociate into sodium, then cyanide. And so this cation, the sodium cation, would indicate to you that this would be a basic solution. So you can look at the components of the salt and look for those alkali or alkaline earth metals, and then some of those common anions like chloride, bromide, iodide, nitrate, or perchlorate. Let's go ahead and look at one more examples before we come up with some good generalizations. So in this example, what we're going to look at is, well, what happens if your salt contains an acid cation and a basic anion? So if we were to look at ammonium carbonate, and at the correct temperature, this would dissociate into ammonium and carbonate. Well, if you were to look up Ka for this first reaction, because this is the dissociation of an acid, Ka of ammonium is equal to 5.8 times 10 to negative 10th. And Kb for carbonate, if we were to look that up, I believe that comes out to be 2.0 times 10 to the negative 4th. So remember, this doesn't have any of those characteristic strong acid or strong base components. Whenever we look at, we don't see any alkali or alkaline earth metals or chloride, but we do see hydronium and hydroxide. So this falls under that example we said, well, weak acid, weak base. Well, it depends on which weak acid and which weak base there actually are as to what the solution is. So here's what we can use. If Ka is greater than Kb, that means the acid is dissociating at a greater extent than the base. The pH will be less than 7, which means it's acidic. If Kb is greater than Ka, that means the base is dissociating at a greater amount than the acid, and the pH is greater than 7, which means that it's basic. Ka and Kb are about the same, then the pH is 7 or around 7, and it's a neutral species. So in this particular example, Ka is on the order of 10 to the negative 10th, Kb is to the order of 10 to the negative 4th. So Kb is greater than Ka, so we could say, without doing any calculations, that this solution would be basic. So let's go ahead and think about some of the factors that can affect the acid strength. So one of the factors is the strength of that covalent bond. So what we'll see is that bond strength is going to be inversely related to the acid strength. Okay, so the strength of an acid is based off of the ability to dissociate. Or instead of ability, let's say extent of dissociation. Okay, so here, the stronger the covalent bond, the weaker the acid, because the stronger the bond is, the more it's going to be hanging on to the proton. So we can just say the stronger the covalent bond, the weaker the acid. Okay, well, there's some other things that we also need to consider besides bond strength, and one of those is the electronegativity. And we can look at this using an electrostatic potential map. So what we can see is as the electronegativity increases, okay, so that difference in the electronegativity between the atoms increases, the acid strength also increases. Well, why is that? Well, think about what electronegativity is telling us. Electronegativity tells us it's the electron tends towards the more electronegative atom. And this means the electrons are not shared evenly. So in the case of HF, the electrons are going to be shifted over towards that fluoride, and then that's going to weaken the bond with hydrogen. So electronegativity and that difference will also lead to a stronger acid strength. So we will go into more quantitative examples as we move forward, but here's a brief introduction to whenever we start to mix acids and bases.